For 65 years, we have been listening to the wrong frequency. That is not a metaphor. It is a literal statement about the history of the search for extraterrestrial intelligence. Since 1960, when astronomer Frank Drake pointed a radio telescope at two nearby stars and heard nothing but static, humanity has been committed to a specific strategy for finding alien civilizations, one that was built on assumptions that made perfect sense in the 1960s and far less sense today. The strategy was simple. Radio waves travel efficiently across interstellar space. We had recently built powerful radio transmitters and receivers. Therefore, aliens probably use radio too. And if they do, they would probably concentrate their signal into a narrow slice of the radio spectrum, so it would stand out from the background noise. So we listened. Dozens of programs over 6 decades, scanning millions of stars across carefully chosen radio frequencies. And we found nothing. Or did we find nothing? Maybe we found nothing because there is nothing to find. Maybe we are alone in the galaxy. That is a genuinely possible answer. But there is another possibility that is only now getting the scientific attention it deserves. Maybe we found nothing because we have been looking in the wrong way, at the wrong frequencies, for the wrong kinds of signals, based on assumptions that were understandable for 1960, but need to be completely reconsidered for 2025. That reconsidering is happening now, and the direction it is pointing is genuinely surprising. The core problem with the old SETI approach is one of assumptions. When Frank Drake started listening for alien signals, humanity had been broadcasting radio waves for only a few decades. We had no idea whether other planets existed around other stars. We could not identify which stars might have habitable worlds, and we had no way to send tightly focused beams of energy across interstellar distances. So we assumed that any alien civilization we might contact would be roughly similar to us, limited in energy, unable to precisely target distant stars, and using radio because that is what we use. Those assumptions are now 65 years out of date on our end, and the aliens, if they exist, have had a lot longer to advance. Here is the central argument that is reshaping modern SETI research. Think about what it means for a technological civilization to be detectable across interstellar distances. To be detectable, they have to be transmitting something powerful enough or structured enough that it can be distinguished from the background noise of the universe across a gap of at least several light years, and likely tens or hundreds of light years. That requires a substantial technological infrastructure. Building and maintaining that infrastructure takes time. Now think about the age of the Milky Way. Our galaxy is roughly 10 billion years old. Technological civilizations capable of interstellar signaling have in principle existed for billions of years before humans arrived. If any such civilization has managed to survive for even 10,000 years after developing the ability to transmit detectable signals, that civilization is 100 times older in its technological phase than we are. If civilizations typically last for 100,000 years, then the average civilization we might contact is 1,000 times more advanced than us. If they last for 1,000,000 years, and why would they not? The gap is enormous. We are, statistically speaking, the newcomers. We are the species that just figured out electricity within the last cosmic blink. Any civilization old enough and advanced enough to be detectable across interstellar distances is almost certainly far ahead of where we are today. This changes everything about what signals we should be looking for. Let us go back to radio and understand why it made sense in 1960 and why it makes less sense now. Radio waves have genuine advantages for interstellar communication. They pass through the dusty regions between stars relatively easily. They were the most accessible form of electromagnetic communication at the time. And there is a specific window in the radio spectrum, a 300 MHz band sitting between a hydrogen emission line and an oxygen emission line, where the natural background noise from the galaxy is at its quietest. Frank Drake called it the waterhole. He reasoned that this natural, quiet spot was the obvious place for interstellar communicators to congregate, the way animals gather at a watering hole. The reasoning was elegant, but it had a fundamental physical problem baked into it that no amount of clever frequency selection could solve. Radio waves are long. The longer the wavelength of an electromagnetic wave, the harder it is to focus into a tight beam. The mathematics of beam focusing is unforgiving. The minimum angular spread of a focused beam is proportional to the wavelength divided by the size of your transmitter. For radio waves, this means that to send a reasonably focused signal to a star 100 light-years away, you would need a transmitting array with a baseline of roughly 1,000 kilometers. With a 1,000-kilometer radio array, a signal aimed at a star 100 light-years distant still spreads out to cover an area 140 billion times the surface area of the Earth by the time it arrives. Think about what that means for the power required. The signal is being diluted across an area 140 billion times larger than its target. To make that signal detectable, you have to pump an almost incomprehensible amount of energy into it. Early SETI theorists thought aliens would solve this problem by concentrating all their energy into a very narrow frequency band, making a spike in the radio spectrum that would stand out above the background. That is the origin of the narrowband radio search strategy that drove SETI for decades. It is a clever but it requires the alien civilization to be doing exactly what we expected them to do, using a strategy chosen specifically to accommodate the limitations of radio technology. What if they are not limited in that way? Laser technology changed the picture dramatically. A laser operates at optical or infrared wavelengths, tens of thousands of times shorter than radio waves. The same mathematics of beam focusing that Hubble's radio becomes a superpower at optical wavelengths. A 1-meter optical aperture or laser array can achieve the same beam collimation as a 1,000-kilometer radio array. A 1-kilometer optical array can focus a beam so precisely that it illuminates not just a star system, but a single planet within that system, across hundreds of light years. In 1960, this was science fiction. In 2025, we have already demonstrated the basic laser physics. We have not built anything at that scale, but we understand the engineering path to it in a way that we absolutely did not understand in 1960, an advanced civilization that has been around for 10,000 years or 1,000,000 years will have worked out that path. They will know how to build tightly focused optical or infrared communication beams. They will not be limited to the shotgun approach of broadcast radio. And if they are not limited to radio, there is no particular reason to assume they are using it. The second major shift in thinking involves targeting, and this is where recent astronomy changes the story in a profound way. When Frank Drake pointed his radio telescope at Tau Ceti and Epsilon Eridani in 1960, those stars were chosen largely because they were nearby and vaguely sun-like. We had no knowledge of whether they had planets. We had no knowledge of whether any star had planets. The question of exoplanet detection was essentially unanswerable with the technology of the time. Today, we know with statistical confidence that essentially every star in the galaxy has planets. We know that Earth-sized planets in the habitable zones of sun-like stars are common. The Kepler Space Telescope survey revealed that roughly 1 in 4 sun-like stars has a planet in the right size range at the right distance to potentially be habitable. We have detected thousands of individual exoplanets and catalogued millions of candidate systems. We know where to look. More importantly, We are on the verge of being able to look directly at those planets, using space-based telescopes with coronagraphs, instruments that block out the overwhelming light of a parent star, combined with sophisticated optical interferometry. Astronomers are developing the technology to take actual images of Earth-like planets around nearby stars, not just detecting their gravitational wobble or the dimming of starlight as they transit, but photographing them, seeing countenance, seeing oceans, detecting in their reflected and emitted light the chemical fingerprints of an active biosphere, oxygen, ozone, methane, in combinations that can only be produced by living organisms. The Habitable Worlds Observatory, currently in development and targeted for operation in the 1930s and 2030s, is designed specifically for this task. It aims to image and characterize Earth-like planets around hundreds of nearby stars, identifying which ones have the atmospheric chemistry consistent with life. Now here is the key point that astronomer Ben Zuckerman has been emphasizing in recent research. If we, with our current technology, are on the verge of being able to identify the inhabited planets in our stellar neighborhood, then a civilization that is 1,000 years or 10,000 years ahead of us has already done this. They already know which worlds in their vicinity bear life. They have already catalogued the biospheres within hundreds of light years, and they have already known about Earth for a very long time. Our technological signals, our radio and television broadcasts, our radar pulses have been spreading outward from Earth for about 100 years. That bubble of radio noise is now 100 light years in radius. Any civilization within 100 light years knows we exist technologically, but an advanced civilization with the ability to image exoplanet atmospheres could have known about life on Earth for far longer. The oxygen and ozone in our atmosphere have been signaling our biological activity for over 2 billion years. They do not need to receive our radio transmissions to know we are here. This means that the old SETI approach of broadcasting into the void and hoping someone is listening was always somewhat backwards. The more likely scenario is that civilizations capable of interstellar communication have already identified Earth as a planet of interest. And if they are sending signals in our direction, they are not sending a broad radio beacon into the void. They are sending a precisely targeted beam aimed at this specific planet because they already know it is worth targeting. That changes what we should be looking for and where. Instead of scanning broad swaths of the radio sky for narrowband signals from unknown directions, the new approach focuses on monitoring specific known targets, stars within a few hundred light years that are likely to have planets capable of supporting technological civilizations, rather than waiting for a civilization to accidentally broadcast into our direction. We monitor the systems most likely to host neighbors that know we are here and might be pointing something at us. This is a much more efficient search strategy, and it opens up the full electromagnetic spectrum rather than just radio. Let us think about energy for a moment, because the energy assumptions of early SETI were also built on the limitations of a 1960 mindset. Early researchers assumed that an alien civilization would be energy constrained in roughly the way we are. They would have a finite power budget and would need to make careful choices about how to use it. That led to the narrowband radio approach. Concentrate all your power into a thin spike, so it stands out. But a civilization that has been around for 100,000 years, or 1,000,000 years, operates at a fundamentally different energy scale. Physicist Nikolai Kardashev formalized this intuition in the 1960s with a scale of civilization types based on energy consumption. A Type 1 civilization harnesses the total energy resources of its home planet. A Type 2 civilization harnesses the energy output of its star. A Type 3 civilization harnesses the energy of its entire galaxy. We are not even a Type 1 civilization yet. We use something like 1/10,000th of the solar energy that reaches Earth, and only a tiny fraction of Earth's total geological energy. We are somewhere around 0.7 on the Kardashev scale. A civilization that has been around for 10,000 years and has had a linear technological development might be approaching Type 2. A civilization a million years old might be Type 2 to Type 3 at Type 2 energy scales. The energy cost of maintaining interstellar communication beams across hundreds of light years becomes manageable. At Type 3 scales, it is trivial. An energy-rich civilization does not need to concentrate all its power into a narrow frequency band. It can broadcast across many frequencies simultaneously. It can maintain multiple beams aimed at multiple star systems at once. It can sustain those transmissions essentially indefinitely. The narrowband radio strategy made sense for our limitations. An advanced civilization does not have our limitations. This means we should not expect the signals we find to look like what we expected. A civilization with abundant energy might send signals across a broad range of frequencies rather than a narrow spike. Those signals might be at optical or infrared wavelengths, not radio. They might be tightly focused on specific planets rather than broadcast widely, and they might be coming from hundreds of light years away rather than just the nearest few dozen stars. Zuckerman's suggested target range is all sun-like stars within about 650 light years. Based on our understanding of stellar populations from the Kepler mission, that volume of space contains roughly 60,000 Earth-like planets orbiting in the habitable zones of sun-like stars. Using conservative estimates about how many of those might actually be habitable in more detailed ways, considering factors like stellar variability, planetary history, geological activity, Zuckerman reduces this to perhaps 600 plausible targets. 600 plausible targets within 650 light years. That is a finite, achievable survey. We can actually monitor those stars. The question is, with what technology, and looking for what kind of signatures? The truth is, we do not know exactly what a technological signal looks like. This is one of the most honest admissions in modern SETI research, and it is also one of the most important. We have a fairly good understanding of what natural sources of electromagnetic radiation produce. Hot gas emits characteristic spectra. Electrons, spiraling in magnetic fields, produce synchrotron radiation with a recognizable signature. Atoms and molecules emit and absorb at specific wavelengths determined by quantum mechanics. All of these are understood and catalogued. A technological signal would stand out as something that cannot be explained by these natural processes. Unusual frequency patterns, anomalous intensity variations, time-dependent modulations that encode information. Rather than following the smooth variations of natural astrophysical processes, a signal from a planet would show a characteristic drift in frequency as the planet moves toward and away from us in its orbit. A Doppler signature that would pin the source to a specific world, around a specific star. We have been teased before. The most famous example is the WOW signal, a strong narrowband radio signal detected at the Big Ear Radio Telescope in Ohio in August of 1977. It had the right characteristics to be an artificial signal from space. It lasted 72 seconds, the duration of a single pass through the telescope's field of view. It was never detected again. Decades later, researchers published a paper suggesting it might have been a hydrogen cloud around a comet. But the debate continues. The discovery of pulsars in 1967 was initially so baffling that the researchers who found them labeled the signals LGM1 through LGM4 for little green men, the regular machine-precise pulsations of a neutron star, spinning hundreds of times per second, looked nothing like anything natural astronomers had seen before. They turned out to be entirely natural. But the story illustrates that we can be surprised by the universe in ways that initially seem technological, modern. SETI is increasingly moving away from waiting for a specific expected signal and toward a more general strategy of anomaly detection. Rather than tuning a telescope to the waterhole frequency and waiting for a narrowband spike, the new approach is to monitor enormous volumes of sky and flag anything that cannot be explained by known natural processes. The definition of a technosignature has broadened from a narrowband radio beacon to any observational signature that implies the existence of technology. This is a more intellectually honest approach. We do not know how an alien civilization thinks. We do not know what communication technologies they use. We do not know whether they are even trying to communicate with us, or whether their technological activity simply leaks signals as a byproduct. We should not design our search around assumptions about alien psychology and aesthetics. The practical enabler of this broader approach is the revolution in astronomical survey capability that is happening right now. Consider what a survey telescope does. A conventional telescope looks at a small patch of sky, studies it in detail, and then moves on. A survey telescope uses a gigantic camera to photograph enormous sections of sky repeatedly, building up a database of how the universe changes over time. Any object that brightens, dims, appears, disappears, or changes in any other way can be automatically flagged for follow-up investigation. The Rubin Observatory, recently completed in the mountains of northern Chile, represents perhaps the most dramatic example of this new capability. Its camera contains 3,200,000,000 pixels and can photograph a patch of sky roughly 40 times the area of the full moon in a single exposure. Over its planned 10-year survey, it will photograph the entire visible southern sky every 3 nights, building up a time-lapse record of several billion astronomical objects. The data flow from this telescope is staggering. 20 terabytes of raw image data every single night. No human being, not even teams of graduate students working round the clock, could examine that data object by object and flag every anomaly. The only way to process it is using automated algorithms that monitor the data, stream in real time, and generate alerts for objects that behave in unexpected ways. This automated alert system was designed for natural astronomical phenomena, supernova, gamma-ray bursts, near-Earth asteroids, variable stars, gravitational lensing events. But the same infrastructure, with relatively modest modifications, becomes a SETI instrument. An alien artifact passing through the solar system would show up in this data. A laser communication beam aimed at Earth that flickered or modulated would leave a signature. A megastructure around a distant star that partially blocked its light in a non-natural pattern would be flagged. An artificial light source on the night side of an exoplanet that appeared when the planet rotated toward us would be detected. In 2024, astronomer Eleanor Gallet and collaborators published a detailed analysis of what the Rubin Observatory might find from a SETI perspective. The conclusion was genuinely exciting. The scale and sensitivity of the survey means that even extraordinarily rare technosignatures would have a chance of being detected if they exist within the survey volume. The observatory will not just be the most powerful natural astronomy instrument ever built for its class of science. It will be the most powerful SETI instrument ever built. Even though SETI is not its primary purpose, this is the concept that researchers now call commensal SETI. The word commensal comes from biology, where it describes a relationship between organisms where one benefits from the other without causing harm. In the SETI context, commensal refers to running a search for technosignatures as a passenger alongside the standard astronomical science being done by major observatories. The survey data is already being collected. The computational infrastructure is already being built. Adding a SETI component requires only the algorithm, development, and the willingness to look. The same logic applies across the electromagnetic spectrum. While Zuckerman's analysis emphasizes optical and infrared wavelengths as the most likely medium for advanced civilizations to use for communication, radio cannot be completely ruled out. Some civilizations might still use radio, and the next generation of radio telescopes will be so powerful that they transform what is detectable in the radio sky. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built by an enormous margin. Its name refers to its total collecting area. It will have roughly 1 square kilometre of radio antenna, spread across 2 continents. It is not a single dish, but an array of thousands of individual antenna elements, connected by fiber optic cables and combined through sophisticated signal processing. This distributed architecture allows it to achieve a sensitivity, an angular resolution that no single physical structure could match. The Square Kilometre Array is expected to reach full sensitivity in the early 2030s. When it does, it will be able to detect an airport radar equivalent at the distance of the nearest stars. It will be able to detect a city's worth of artificial radio leakage at several light years. More powerfully, it will be able to survey the entire radio sky continuously, with the data flow exceeding even the Rubin Observatory's prodigious output. The Square Kilometre Array generates as much data in a single second as the Rubin Observatory generates in an entire night. The challenge, as with Rubin, is computational. You cannot store all of that data. You cannot examine it pixel by pixel. You need real-time algorithms that can identify the needles in the haystack without requiring the haystack to be physically stored anywhere. Research teams have been working for years on developing the right algorithms for the Square Kilometre Array, both for natural astrophysics and for SETI. The progress has been substantial, and the computational architecture that will process Square Kilometre Array data is being designed with SETI applications explicitly in mind. Beyond radio and optical surveys, there is another class of technosignature that is gaining increasing attention: the physical byproducts of advanced technology. A sufficiently advanced civilization does not just transmit electromagnetic signals. It builds things. It consumes energy at large scales. It modifies its environment. Those activities leave physical traces that might be detectable across interstellar distances. The most dramatic version of this idea involves Dyson structures, hypothetical megastructures built by civilizations to capture the energy output of their stars. A civilization on a Kardashev Type 2 trajectory would eventually harvest so much of their star's energy that their stellar system would begin to look different from a natural stellar system. The star's optical output would decrease while its infrared output increased, as the captured energy was converted to other uses and re-radiated as waste heat. This distinctive pattern in the energy output of a star, dimmer in visible light, brighter in the infrared than it could be detectable across thousands of light years with current and near-future telescopes. Systematic searches for this kind of infrared excess around nearby stars have been conducted using data from the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer. So far, nothing definitively unnatural has been found, but the surveys were not exhaustive, and the sensitivity required to detect partial Dyson structures is much higher than what was needed for the searches that had been done. Future infrared observatories will do much better. A more subtle variation on this idea involves partial occulters structures in orbit around a star that partially block its light in ways that do not match the smooth, transit-shaped dip you get from a planet or moon. In 2015, A paper by Tabitha Boyajian and collaborators described a star, now known as Boyajian's star, or the WTF star, where WTF stands for Where's the Flux, that showed dramatic, irregular dimming events, including one episode where the star's brightness dropped by over 20%. Natural explanations were proposed and debated. The best current explanation involves a swarm of cometary fragments, though this remains uncertain. It was not the alien megastructure that some popular media suggested, but the episode illustrated both how weird natural systems can be and how our observing capabilities are now good, enough to catch genuinely unusual stellar behavior. The infrastructure being built for natural, astronomical surveys will catch these anomalies automatically. The Rubin Observatory's 3-night cadence across the southern sky means that any star exhibiting unusual dimming behavior will be flagged within days. The algorithms designed to catch supernova will also catch anything else that changes in an unexpected way. There is also the question of signals in existing data. One of the most interesting ideas in modern SETI is the possibility that we have already received a technosignature, and it is sitting in a data archive waiting to be recognized. Multiple large-scale astronomical surveys have been running for years, collecting data on millions and eventually billions of objects. The HARPS Planet Hunting Survey, for example, uses a spectrograph on a telescope in Chile to search for the tiny Doppler wobble that planets induce in a star's radial velocity. This dataset covers thousands of stars observed repeatedly over many years. In a study published recently, astronomers Benjamin Fields and Jason Goodman showed that the HARPS data would actually be sensitive to optical laser communication beams from planets around the observed stars. The laser light would appear as an anomalous spike in the stellar spectrum, a sharp excess at a specific wavelength that would not match any natural spectral feature. They did not find anything in the existing data, but the demonstration that existing archival data could contain technosignatures is significant. It means that SETI is not only about future observations, it is also about reanalyzing past observations with new algorithms. Machine learning techniques are particularly promising here. Traditional signal detection algorithms are designed to look for specific expected patterns. Machine learning systems can be trained to recognize anomalies without being told in advance what the anomaly will look like. They learn what normal looks like from the training data and flag whatever does not fit that normal distribution. This approach is much better suited to the genuine uncertainty of SETI. We do not know what we are looking for, so we should use tools that do not require us to specify in advance what we are looking for. Several research groups are now working on machine learning-based anomaly detection for SETI applications. The theoretical frameworks for what kinds of anomalies might indicate technology are being developed in parallel. The field is moving from targeted searches based on specific expected signals toward comprehensive, model-agnostic surveys of the electromagnetic sky for anything that defies natural explanation. One aspect of this discussion that deserves more attention is what we might call the demographics of the search. Different SETI strategies have very different sensitivities to different types of civilizations. Narrowband radio searches are most sensitive to civilizations that are deliberately beaming radio signals in our direction. Anomaly detection surveys are most sensitive to civilizations whose technology leaks measurable byproducts even without deliberate signaling. Infrared excess searches are most sensitive to civilizations that have reached Kardashev type 2 or above. The reason this matters is that we want to avoid selection effects. If our search is only sensitive to one type of civilization, we might incorrectly conclude that civilization is common or rare based only on our detection efficiency for that specific type. A comprehensive SETI program needs multiple complementary strategies running simultaneously. each sensitive to different types of signatures, so that the results can be interpreted coherently. Current and near-future surveys are, almost accidentally, achieving this comprehensiveness. The Rubin Observatory's optical survey is sensitive to transient phenomena, unusual stellar behavior, and anomalous objects in our own solar system. The Square Kilometer Arrays Radio survey is sensitive to radio-transmitting civilizations and to the radio leakage of technological activity. Future infrared space telescopes will be sensitive to the waste heat signatures of energy-intensive civilizations. The Habitable Worlds Observatory will be sensitive to the atmospheric biosignatures of inhabited planets. Together, these instruments cover a wider range of possible technosignature types than any previous combination of SETI programs, and they are all doing this science whether SETI is explicitly mentioned as a goal or not. That is the essence of commensal SETI. The universe is being mapped in unprecedented detail. The maps will contain SETI information by default. Let us step back and appreciate the scale of what we are attempting. The Milky Way galaxy is roughly 100,000 light-years in diameter. It contains somewhere between 100 billion and 400 billion stars. The region within 650 light-years of Earth, the volume that Zuckerman proposes monitoring, contains roughly 150,000 stars. Of those, roughly 1 in 5 are Sun-like enough to potentially host Earth-like planets. That gives us perhaps 30,000 stars to prioritize, containing perhaps 60,000 candidate habitable planets. 650 light-years sounds enormous. It is enormous by human standards, but it is less than 1% of the way across the Milky Way. We are proposing to examine our immediate stellar neighborhood, cosmically speaking. If intelligent life is common in the galaxy, there should be multiple civilizations within this range. If intelligent life is rare, but the galaxy has a long history, the few civilizations that exist might be scattered far apart, and might not include any within our immediate neighborhood. The fundamental uncertainty that motivates SETI in the first place is still unresolved. We do not know whether life is common or rare in the universe. We do not know whether complex multicellular life is common or rare among worlds with any life. We do not know whether intelligence evolves commonly from complex life. We do not know whether technological civilization is a typical outcome of intelligence or a rare and fragile accident. These uncertainties stack multiplicatively. If each step is even somewhat probable, the galaxy could be teeming with intelligent life. If any step is very improbable, we might be alone, not just in the Milky Way, but in the observable universe. The Drake equation, which Frank Drake himself wrote on a blackboard at the first SETI conference in Green Bank, West Virginia, in November of 1961, was never meant to give a precise answer to these questions. It was meant to organize our ignorance into a form that allowed productive discussion. It identifies the key unknowns and forces us to estimate them, even when our estimates span orders of magnitude. Different scientists plugging in their best guesses for the equations, factors have gotten answers ranging from essentially zero civilizations in the observable universe to millions in the Milky Way alone. We have made enormous progress in estimating some of the Drake equations factors since 1961. We now know the rate of star formation in the galaxy to reasonable precision. We now know the fraction of stars with planets, essentially all of them. We now know the fraction of planets in habitable zones that are Earth-sized, a substantial fraction of those stars. These factors are no longer wildcards, but the biological and sociological factors remain deeply uncertain. What fraction of habitable planets actually develop life? What fraction of those develop intelligence? What fraction of intelligent species become technological? How long does a technological civilization typically survive? We have exactly one data point for all of these questions: Earth. and trying to draw statistical conclusions from a single data point is not really possible. This is why the search matters. Every negative result tightens the constraints on some of those unknown factors, even if it does not answer them definitively. Every positive result, even a single confirmed detection of a technosignature, would transform our understanding of life's place in the universe in a way that no amount of theoretical calculation could. The philosophical and scientific stakes are enormous. If we detect evidence of another technological civilization, even a subtle signal in a surveyed dataset that requires months of careful analysis to confirm, the implications cascade outward through almost every domain of human thought. It would mean that the emergence of intelligence is not a singular accident of Earth's history, but a repeatable outcome of physical processes that occur across the galaxy. It would tell us that technological civilizations can survive long enough to be detectable, providing at least one data point for the longevity factor that Drake's equation desperately needs. It would raise immediate practical questions about what kind of civilization this is, how far away it is, what they know, and whether communication across the distance separating us is feasible on timescales relevant to human civilization. And if decades of increasingly comprehensive surveys continue to find nothing, that too is a scientifically important result. A confirmed absence of technosignatures across the full sky, across all wavelengths, to the sensitivity limits of our instruments, would provide genuine evidence for one of several disturbing conclusions: that intelligence is very rare, that technological civilizations are that advanced civilizations deliberately hide themselves, or that we are missing something fundamental about what technosignatures look like. None of these conclusions would be comfortable, but discomfort is not a reason to avoid honest science. The question of whether we are alone in the universe is arguably the most profound question humanity can ask. It deserves the most powerful scientific tools we can bring to bear on it. Those tools are now arriving. The Rubin Observatory is operational. The Square Kilometre Array is under construction. The Habitable Worlds Observatory is in development. Algorithms for anomaly detection, powered by machine learning systems that grow more capable with each passing year, are being deployed on existing datasets and designed for future ones. The next decade will see more data collected about the sky than in all of previous human history combined. Some of that data will tell us about the lives and deaths of stars. Some of it will map the large-scale structure of the universe. Some of it will tell us about dark matter and dark energy and the ultimate fate of the cosmos. But some of it, and we do not know how much, might tell us whether the light from other worlds contains the fingerprints of intelligence. The search is becoming more sophisticated, more sensitive, more comprehensive, and more theoretically grounded than it has ever been before. The assumptions that drove SETI for its first 60 years are being rigorously examined and updated. The narrowband radio focus is giving way to a full-spectrum, anomaly detection approach. The fantasy of a deliberate alien beacon aimed at Earth is being supplemented by the harder work of looking for inadvertent signatures of advanced technology. The specific targets of the search are being refined by the explosion in exoplanet science that tells us where the most plausible candidate worlds actually are. We still do not know the answer. We may not know for decades. We may find it in a dataset collected last year, hiding in an archive until a clever algorithm notices the anomaly that human eyes overlooked. We may find it in the first images from the Habitable Worlds Observatory, in the atmospheric spectrum of a world 400 trillion kilometers from Earth, or we may find that the universe continues to be silent on this question, and that silence will force us to grapple with what it means. The scientific community that pioneered this search spent 60 years listening to a frequency that might have been chosen for entirely the wrong reasons. The next generation is listening everywhere, to everything, with instruments that would have seemed like science fiction to Frank Drake. The search for minds beyond Earth is no longer a fringe endeavor conducted on borrowed telescope time. It is woven into the fabric of modern astronomy. Itself, whatever we find or do not find, we will understand our place in the universe more clearly because of it. If you found this exploration of one of science's deepest questions worthwhile, consider sharing it with someone who would appreciate it, and follow along as this story continues to develop. The next chapter in the search for intelligence beyond Earth is just beginning, and the evidence, whatever form it takes, is almost certainly already out there waiting to be found. The universe is roughly 13.8 billion years old. Intelligent life on Earth has been looking up at the sky with curiosity for perhaps 100,000 years. We have been pointing instruments at it with scientific intent for a few hundred years. We have been capable of interstellar communication for about 100 years. In the context of cosmic time, we just arrived. And the question of whether anyone was here before us, whether anyone is here with us now, in the same galaxy, looking up at the same stars and wondering the same thing remains. For the moment, beautifully, frustratingly, compellingly open, the search goes on, and for the first time in its history, the tools are finally catching up to the ambition to understand why this moment in SETI history feels genuinely different. It helps to trace exactly where the old assumptions came from and why they were so persistent. The 1960s were a remarkable period in human technological history. In the span of a decade, humanity went from launching the first artificial satellite to landing people on the moon. Radio. Astronomy was a young and rapidly advancing field. The discovery that hydrogen in interstellar space emits radio waves at a very specific frequency, 21 centimeters, or 1400 megahertz, had been made only about a decade before Drake's first search. This hydrogen line was a natural milestone, a universal signpost written into atomic physics that any civilization with radio technology would inevitably encounter. Drake's reasoning for the water hole specifically was built on this idea of universality. The hydrogen line and the hydroxyl line together define a natural quiet window in the radio spectrum. Any civilization that understands atomic physics anywhere in the universe would discover these same lines. The gap between them, which Drake poetically called the water hole, seemed like the cosmically obvious meeting place for communicating civilizations. If you were trying to signal someone you had never met, and both of you knew atomic physics, why not use the frequency band that atomic physics itself draws attention to? There is something genuinely beautiful about this reasoning. It is the kind of thinking that makes science satisfying, taking fundamental physical laws and asking what patterns they would impose on intelligent behavior across the universe. And it was not obviously wrong. It might still be right. Some civilizations might still use the water hole frequency for exactly the reasons Drake imagined. But 60 years of searching that frequency range without success is not nothing. The absence of confirmed detections does not prove the signal is not there. We have not searched anything close to the full sky at the sensitivity needed to rule it out, but it does shift the prior probabilities enough to take seriously the possibility that the waterhole strategy, however elegant, is not the right one. One useful way to think about this is to consider the history of human communication itself. In the middle of the 19th century, the telegraph was the cutting edge of long-distance communication. Anyone trying to predict how civilizations would communicate across large distances in the year 1960 would have been working from the best available technology of their era and might have predicted something like a global network of telegraph cables. And in 1960, telephone cables were indeed a major communication infrastructure. which would seem to vindicate the prediction. But by 2025, physical cables carry data rather than voice. Wireless communication saturates the spectrum. Fiber optics carry the bulk of internet traffic, and satellite constellations provide global coverage. The assumptions of the telegraph era, while not entirely wrong, missed most of the important developments. The lesson is that predicting how technological civilizations will communicate is genuinely difficult, because communication technology changes rapidly, and the changes are not always predictable from first principles. This does not mean the search is hopeless. It means we should search as broadly as possible and remain genuinely open to finding signals in unexpected places. The physical constraints at least give us some guidance. Electromagnetic waves are the most efficient way known to physics to transfer information across interstellar distances. Nothing travels faster than light. Alternative approaches, sending physical probes, using gravitational waves, communicating through quantum entanglement, all face severe practical limitations for interstellar distances. Gravitational wave communication would require catastrophic astrophysical events as transmitters. Quantum entanglement cannot transfer information faster than light. Physical probes take centuries to millennia to cross even the nearest stellar distances, so electromagnetic communication is almost certainly the primary channel for any interstellar signaling. Even among advanced civilizations, the question is which part of the electromagnetic spectrum, and here the physics provides real guidance, not just speculation. The electromagnetic spectrum spans an enormous range, from radio waves hundreds of meters long to gamma rays, with wavelengths shorter than an atomic nucleus. For interstellar communication, some parts of this spectrum are immediately eliminated. Gamma rays and X-rays are absorbed by interstellar gas and dust. Very low-frequency radio waves below about 10 MHz are reflected by planetary ionospheres and do not propagate well in interstellar space. The remaining window, from roughly tens of megahertz to hundreds of terahertz, encompasses the radio bands, microwaves, infrared, and visible light. Within this window, the trade-offs are real. Radio waves propagate well through the dusty interstellar medium. Optical and infrared waves are blocked by dust clouds. Though along many lines of sight through the galaxy, the blocking is modest. Radio signals are harder to focus. Optical signals are much easier to focus. The interstellar scintillation that causes radio waves to twinkle affects radio communication differently from optical communication. Any sufficiently advanced civilization will have worked through these trade-offs in detail. One factor that often gets overlooked in popular discussions is the background noise environment. Radio communication is fundamentally a signal-to-noise problem. The signal has to stand out above the noise in the receiver. In space, the noise environment has two components: the noise generated by the receiving equipment itself, and the noise from the cosmic background, radio emission from the galaxy, and the cosmic microwave background. At certain radio frequencies, this cosmic background is much quieter than at others, which is exactly what Frank Drake was exploiting with the waterhole concept. But the same physics applies to optical and infrared communication. The sky between stars in the infrared and optical is much quieter than the radio sky in terms of competing signals. A focused laser beam at optical wavelengths can achieve a signal-to-noise ratio that is genuinely competitive with or superior to the best radio approaches, especially for targeted point-to-point communication. An advanced civilization with the technology to build tightly focused optical beams would recognize this. Moreover, the information density possible in optical communication is vastly higher than in radio communication. The frequency of visible light is roughly 100,000 times higher than typical radio communication frequencies. Since the information capacity of a communication channel is proportional to the bandwidth relative to the carrier frequency, and since high-frequency carrier waves support higher bandwidth, optical communication can in principle carry 100,000 times more information than radio for the same channel characteristics. For a civilization transmitting encyclopedias of information about themselves, their science, and their history, this matters. There is also the question of power efficiency. A laser at optical wavelengths can be extremely efficient at converting electrical power into coherent electromagnetic radiation. Modern high-power lasers can approach 30 to 40% wall plug efficiency, combined with the tighter beam collimation possible at optical wavelengths. An optical communication system can deliver more bits of information per watt of input power over interstellar distances than any practical radio system. For a civilization that cares about energy, efficiency, and any civilization that has survived long enough to develop, interstellar communication presumably cares about energy efficiency. This is a compelling advantage. None of this means radio SETI is pointless. As already discussed, the square kilometer array is going to achieve sensitivities far beyond anything previously possible. And there is genuine scientific value in ruling out radio technosignatures at high sensitivity, even if the eventual conclusion is that advanced civilizations prefer other communication channels. But the argument for expanding SETI beyond radio is solid, and the technology to conduct optical and infrared SETI searches is now available in a way it was not. Even 20 years ago, the search for optical technosignatures has been gaining momentum since the late 1990s. The SETI Institute launched the first systematic optical SETI program in 2001 at the Lick Observatory in California, searching for short nanosecond-scale pulses of light, the kind of signal that a powerful laser communication system might produce from hundreds of nearby stars. More recently, Breakthrough Listen, the privately funded SETI initiative launched in 2015 with $100 million in funding, has dedicated significant effort to both radio and optical SETI searches. Breakthrough Listen has conducted the most sensitive searches to date at multiple wavelengths, including optical. The Automated Planet Finder telescope at Lick Observatory has been repurposed part of the time for optical SETI observations. The Unistellar network of citizen-owned smart telescopes has been deployed for coordinated optical SETI campaigns. The Panoramic SETI project has developed a full-sky optical transient monitor specifically designed to catch brief laser pulses from anywhere in the sky simultaneously. These are not science fiction concepts, they are operating instruments. And that brings us to one of the most exciting developments in the field, which is the integration of machine learning into anomaly detection at scale. The challenge of looking for anomalies in astronomical data has historically been limited by human bandwidth. A skilled astronomer can review maybe a few thousand light curves, graphs of how a star's brightness varies over time in a working year. The Rubin Observatory will generate light curves for billions of objects. Even 10,000 skilled astronomers could not manually review the data, but machine learning models can be trained to do this at computer speed. The challenge is subtle. A supervised machine learning model learns to classify things into categories based on labeled training examples. But we do not have labeled examples of technosignatures. We have never detected one. So the training problem is different from standard classification. Instead, models are being developed to learn what normal looks like for each class of astronomical object, what a normal variable star looks like, what a normal eclipsing binary looks like, what a normal quasar looks like, and then flag anything that does not fit any of the known categories. This is called anomaly detection or novelty detection in machine learning terminology. and it is an active research area both within astronomy and in the broader machine learning community. The methods include autoencoders, isolation forests, variational autoencoders, and other unsupervised or semi-supervised architectures. They are being tested on existing astronomical datasets to characterize their performance before the full deluge of Rubin data arrives. The results so far are promising. These methods are recovering known interesting objects in archival data and flagging new anomalies that turn out to be interesting but natural phenomena, unusual stellar evolutionary states, exotic binary star configurations, strange transient events. The same algorithms, with appropriate tuning, will be looking at that same data for signatures that cannot be explained by any known natural process. There is also an entirely separate class of technosignatures search that has received less attention but may prove equally important, looking not for communication signals but for evidence of technology in the atmospheres of exoplanets. When astronomers study the atmosphere of an exoplanet, they typically do so through transmission spectroscopy, measuring the spectrum of starlight that filters through the planet's atmosphere as the planet crosses in front of its star. Different molecules absorb light at different characteristic wavelengths, leaving distinctive fingerprints in the spectrum. Oxygen, ozone, water vapor, carbon dioxide, methane, each has a signature that can be identified. Now consider what the industrial civilization of Earth has done to our own atmosphere over the last 200 years. We have increased the concentration of carbon dioxide by roughly 50% above pre-industrial levels. We have created entirely new molecules that do not exist in nature, chlorofluorocarbons, which persisted in the atmosphere for decades before international agreements banned their production. We have released nitrogen compounds and sulfur compounds at scales that have measurably altered the atmospheric chemistry. Globally, if astronomers in another stellar system were observing Earth from across interstellar distances using a sufficiently powerful they would notice that our atmosphere has an unusual amount of carbon dioxide for a planet with life. Life normally cycles carbon dioxide efficiently. They might detect the chlorofluorocarbons, which have essentially no natural source and whose presence in an atmosphere is a strong indicator of industrial chemistry. They might detect unusual combinations of gases that indicate a biosphere under industrial stress. This is a new kind of technosignature, not a deliberate signal, not a megastructure, not a laser beam, but the inadvertent pollution signature of a technological civilization altering its own atmosphere. The James Webb Space Telescope is now doing transmission spectroscopy on exoplanet atmospheres. Its successor, the Habitable Worlds Observatory, will be able to study the atmospheres of Earth-sized planets around Sun-like stars in the habitable zone, looking for industrial pollution signatures in those atmospheres. Is now a scientifically serious proposal. The philosophical dimension of this search is striking. If we detected chlorofluorocarbons in the atmosphere of an exoplanet, we would know that civilization was in its early industrial phase, the phase equivalent to our late 20th century, before the Montreal Protocol. That detection would tell us not only that technological life exists there, but also something about the stage of its development. We would be reading the environmental signature of an industrial society at a particular moment in its history, preserved in its atmosphere, readable from across the light years. The idea that we might detect another civilization through its pollution, through the atmospheric evidence of its technological success and potentially its technological overreach, is one of those ideas that seems like something from a science fiction novel, but is now a real topic in peer-reviewed astronomy journals beyond individual technosignatures. Researchers have also begun thinking about what an entire interstellar civilization would look like at galactic scales. The physicist Michael Hart and later Frank Tipler argued that any sufficiently advanced civilization would, over millions of years, spread outward from its home world through interstellar colonization, even at speeds much slower than light. A civilization that colonizes nearby star systems, and those colonies in turn colonize further systems, would spread across the entire Milky Way in perhaps 10 to 100 million years, a tiny fraction of the galaxy's age. The implication is that if any technological civilization anywhere in the Milky Way had developed space colonization and the drive to use it, we would expect the entire galaxy to be colonized by now. The fact that Earth does not appear to be colonized, combined with the absence of obvious civilizational signatures across the galaxy, has been called the Fermi paradox, named for physicist Enrico Fermi, who reportedly asked during a lunch conversation with colleagues in 1950, simply, "Where is everybody?" The Fermi paradox is not just a philosophical curiosity. It is a genuine scientific puzzle with real observational content. If fast-spreading interstellar civilizations are common, we should see evidence of them. We do not see obvious evidence. Either such civilizations are not common, or they exist but spread in ways that are not obvious. Or there is something about the physics of interstellar colonization that makes it much harder than it sounds. Or advanced civilizations consistently make choices that prevent or limit such spread. Or perhaps the most unsettling possibility, there is some systematic factor that eliminates technological civilizations before they reach the colonization stage. These proposed explanations are collectively known as Fermi paradox resolutions, and there are dozens of them in the literature. Some are optimistic. Perhaps the universe is young enough that we are genuinely among the first technological civilizations to arise. Others are sobering. Perhaps the development of nuclear weapons, or artificial intelligence, or biotechnology presents a filter that most technological civilizations do not survive. Others are strange. Perhaps advanced civilizations migrate to virtual realities and have no interest in physical expansion. Perhaps they deliberately hide their signatures to avoid disturbing emerging civilizations like ours. The new observational campaigns now beginning cannot definitively resolve the Fermi paradox, but they can constrain it. A comprehensive all-sky survey that finds no technosignatures to certain sensitivity limits puts upper bounds on the prevalence of various types of advanced civilizations. If we find nothing in the full Rubin Observatory survey across 10 years, that is more constraining than 60 years of targeted radio searches by orders of magnitude in terms of the volume surveyed and the types of signatures searched. If we find something, the paradox resolves itself. The interaction between SETI and the broader fields of astrobiology and exoplanet science has also matured substantially in recent years. These fields have historically been somewhat separate. Astrobiology focuses on the origin and prevalence of life in general, while SETI focuses specifically on technological intelligence. But they share foundational questions and increasingly share observational infrastructure. The discovery of the first exoplanet around a sun-like star in 1995-51, Pegasi b, a massive gas giant orbiting impossibly close to its star, detected through its gravitational wobble, transformed both fields. Before that discovery, the prevalence of planets around other stars was genuinely uncertain enough that serious scientists could argue that planetary systems might be rare. After 1995, and especially after the Kepler mission results beginning around 2012, that uncertainty collapsed. Planetary systems are ubiquitous. The question is no longer whether other planets exist, but what they are like. and whether they bear life. The astrobiology community has organized around a tiered search strategy. First, identify which worlds could in principle support life, the habitable zone, planets with appropriate size and composition. Second, study those worlds' atmospheres for the chemical signatures of biological activity. Third, look for signatures of technological civilization among the worlds already identified as biologically active. This three-step strategy makes enormous scientific sense. A world with biosignatures but no technosignatures might be inhabited by organisms that never developed technology, or whose technology is not yet advanced enough to produce detectable signatures, or whose technological period has passed. A world with both biosignatures and technosignatures is as close to a confirmed detection as we could get, without sending a probe. The Habitable Worlds Observatory, the flagship mission concept currently being developed by the astronomy community and expected to be recommended in the upcoming decadal survey of astronomy priorities, is designed to carry out the first two steps of this strategy. It aims to image dozens of nearby potentially habitable worlds and characterize their atmospheres in enough detail to detect oxygen-ozone combinations, which on Earth are a strong indicator of photosynthetic life, as well as to detect the simultaneous presence of reactive gases like oxygen and methane that can only coexist in an atmosphere maintained by active biology. If the Habitable Worlds Observatory finds a planet with clear that world immediately becomes the most compelling SETI target in the known universe. Every available radio telescope, optical telescope, and space telescope would be brought to bear on it. The world's astronomical community would focus enormous resources on that system, looking for any additional signature of technology. Every anomaly in its atmospheric spectrum, every unusual dimming of its parent star, every unusual pattern in its infrared emission would be scrutinized with unprecedented care. This is the scenario that researchers hope for, not a sudden, unambiguous beacon from deep space, but a growing body of evidence converging on a particular world, with biosignatures confirmed first and then a patient, careful search for the overlay of technological signatures on top of the biological ones. The timeline for all of this is not infinite. The Rubin Observatory is already in operation, beginning its 10-year survey. The square-kilometer array will reach significant sensitivity in the late 2020s and achieve its full capability in the early 2030s. The Habitable Worlds Observatory, if funded and developed on its current trajectory, might achieve first light in the early to mid-2030s. Breakthrough Listen continues its radio and optical surveys in the present. This means that the next 15 to 20 years represent, in an important sense, the most serious SETI effort in human history. Not a dedicated search by a handful of enthusiasts with borrowed telescope time, but a coordinated investigation embedded in the mainstream of astronomical research, with instruments that dwarf anything previously available, and with computational tools sophisticated enough to make sense of the resulting data. If we find something in this period, we will know. If we find nothing, we will have the most powerful negative result in the history of the search, which will itself tell us something important about how life and intelligence are distributed in the universe. What makes this moment unique in the history of the search is not merely the power of the instruments, though that is genuinely transformative. What makes it unique is the coherence of the strategy. For the first time, astronomers who study exoplanets, astronomers who study stellar astrophysics, astrobiologists who study the conditions for life, and SETI researchers who search for technosignatures are all working with overlapping data, shared theoretical frameworks, and converging observational goals. The silos are breaking down. The accidental SETI that comes from natural astronomy surveys is being embraced rather than resisted. The question of life in the universe is being treated as a mainstream scientific question rather than a fringe. Curiosity. Frank Drake had a vision in 1960. He pointed a telescope at two nearby stars and listened. He heard nothing but static and wondered what it meant. That question has echoed through 60 years of scientific effort. The people who carried it forward were sometimes regarded as eccentric, sometimes marginalized, sometimes regarded as wasting time that could be spent on more tractable problems. They were patient. They kept listening. They refined their methods, expanded their searches, and built the theoretical frameworks that are now enabling a genuinely new approach. And now, without necessarily intending to, the entire astronomical community has joined the search. Every survey telescope is a SETI instrument. Every exoplanet catalogue is a list of potential targets. Every atmospheric spectrum is a potential biosignature or technosignature waiting to be read. The universe is not infinite in the observational sense. Every observation gives us data. Every data point constrains what is possible. Every survey narrows the space of uncertainty. Over the next 2 decades, we will constrain the question of intelligent life in the universe more tightly than in all of previous human history combined. We still do not know the answer. We may be the only minds in the Milky Way, or the nearest civilization may be 600 light years away, already aware of Earth's biosphere, already sending a signal we have not yet built the tools to detect, and now we are building them. The truth is somewhere in that range of possibilities, and science is, for the first time, genuinely capable of beginning to find out which one it is. The search has never been more serious. The tools have never been more powerful. And the fundamental question, are we alone, has never been more amenable to an actual scientific answer. That is where we are. And that is why this moment, above all previous moments in the history of the search, is the one worth paying attention to appreciate how far we have come in the underlying science that supports the search. Consider the history of our understanding of planetary systems. When Drake conducted his first search in 1960, the existence of planets around other stars was entirely theoretical. No confirmed exoplanet existed. The detection of another solar system was a problem considered so technically challenging that many astronomers of the era thought it might never be solved with ground-based telescopes. First confirmed detection of planets around another star came in 1992, not around a sun-like star, but around a pulsar. Astronomer Alexander Volshin and Dale Frail, working with the Arecibo radio telescope in Puerto Rico, detected timing variations in the pulsations of a millisecond pulsar that could only be explained by planets orbiting it. These planets, in one of science's great ironies, orbited a stellar corpse, the remnant of a star that had exploded as a supernova. Any life that might have existed in that system was almost certainly exterminated by the explosion. But the discovery demonstrated that planets could form in unexpected places, and that their gravitational influence on their parent star was detectable. 3 years later, in 1995, Michel Mayor and Didier Queloz announced the detection of the first planet around a main sequence star, a normal hydrogen-burning star like our Sun. The planet was 51 Pegasi b, a gas giant with half the mass of Jupiter orbiting its star in 4.23 days. For comparison, Mercury takes 88 days to orbit the Sun. 51 Pegasi b was impossibly close to its star by the standards of our solar system, receiving 2,000 times more stellar radiation than Earth receives from the Sun. This discovery was profoundly surprising, not because it confirmed that other planets exist, that was expected theoretically, but because of how different the first planet found was from anything in our own solar system. The planet hunters had expected to find something more like our own solar system, with small rocky worlds close in and large gas giants further out. Instead, they found what became known as a hot Jupiter, a gas giant in an orbit where no gas giant should form. According to the prevailing theories of planetary formation, the discovery of hot Jupiters forced a complete revision of planetary formation theory. If gas giants could be found that close to their parent stars, the migration of planets during formation must be far more violent and dynamic than previously imagined. The orbital architectures of planetary systems turned out to be far more diverse than anyone had anticipated. This diversity has profound implications for SETI. If planetary systems come in an enormous variety of configurations, the fraction of them with stable, habitable conditions for the development of life over billions of years may be smaller or larger than simple models suggested. The details of how a planetary system formed and evolved determine which planets spend time in the habitable zone, how stable their orbits are, whether they have giant planet neighbors that prevent catastrophic impacts or cause them, whether they have large moons that stabilize their axial tilt, and dozens of other factors that may affect habitability. Earth benefits from an unusually fortunate set of circumstances that we are only now fully appreciating. Our moon, which formed from a giant impact early in Earth's history, stabilizes Earth's axial tilt to within a few degrees over millions of years. Without this stabilization, Earth's axial tilt could vary chaotically from near zero to extreme values, causing climate swings far more severe than anything in our geological record. Jupiter's gravity clears much of the outer solar system of planet-crossing debris that might otherwise pummel the inner planets continuously. The relative calm of Earth's recent geological history, which has allowed complex land-dwelling life to flourish, may be partly due to these fortunate coincidences. Does this mean that Earth-like conditions are rare? Not necessarily. It means they may require specific architectural features in a planetary system, and understanding which features are required and how common those features are is a major scientific goal for the coming decades. The Rubin Observatory survey will provide enormous statistical samples of planetary system architectures. The Habitable Worlds Observatory will directly image nearby habitable zone planets. Together, these observations will constrain the fraction of stars that have genuinely Earth-like planets. The history of life on Earth adds another layer of complexity. Life appears in the geological record remarkably quickly after conditions became suitable within a few 100 million years of the end of the heavy bombardment phase about 3.8 billion years ago. This rapid appearance of life suggests that the emergence of life, once the right chemical conditions exist, may be rapid and nearly inevitable. But the transition from simple microbial life to complex, multicellular life took another 2 billion years, and the transition from multicellular life to intelligence, and from intelligence to technology, happened only in the last several 100 million years. This timeline suggests that while the origin of life might be common, the development of technological intelligence might be rare, requiring an extraordinary combination of circumstances and an enormous amount of time. Or it might suggest that technological intelligence, once it develops, tends to develop relatively late in a planet's habitable lifetime, when the environmental conditions have had enough time to become complex and varied enough to drive the evolution of sophistication, cognitive capabilities. In that case, the scarcity of technological civilizations we seem to observe might simply reflect the fact that the galaxy is just now old enough for significant numbers of them to have developed. This interpretation, sometimes called the early Earth hypothesis, suggests that we might be among the first technological civilizations in the Milky Way, not because intelligence is inherently rare, but because the universe has simply not had enough time yet to produce large numbers of them. The Milky Way is roughly 10 billion years old. but the conditions for rocky planet formation required the previous generations of stars to explode and distribute heavy elements into the interstellar medium. The first stars were composed entirely of hydrogen and helium. Rocky planets require silicon, iron, carbon, and other elements that only form in stellar interiors and are distributed by stellar deaths. The chemical enrichment of the galaxy has been a gradual process. The stellar populations in our neighborhood reached the metallicity needed for Earth-like rocky planets perhaps 5 to 8 billion years ago. Earth itself formed 4.54 billion years ago, at a time when the galaxy had become chemically rich enough to support it. If the minimum time from planetary formation to technological civilization is something like 4 to 5 billion years, as it was on Earth then, only planets that formed early in the galaxy's history have had enough time to develop technological civilizations, and those planets are not numerous. This argument is speculative, but grounded in real constraints from stellar astrophysics and geochemistry. It suggests that the apparent silence of the universe might be more about timing than about the rarity of intelligence. We might be living in the era when the first wave of technological civilizations is just now beginning to emerge across the galaxy, making the universe look quiet from the perspective of any one of them. If this is correct, then the SETI surveys now beginning are extraordinarily timely. They are starting at the moment when, if this hypothesis is right, the galaxy is beginning to fill with minds. A negative result from the current generation of surveys would be consistent with this hypothesis. A positive result would vindicate it spectacularly. The question of what an alien civilization would actually want to do, whether they would want to communicate, whether they would have any interest in us, whether they would be aware of our existence, is one that SETI researchers generally try to avoid speculating about too extensively, for good reason. We have exactly one example of a technological civilization, and drawing universal conclusions about alien psychology from a sample size of one is not scientifically reliable. But some general principles can be argued. Any civilization advanced enough to detect our existence and technological enough to direct signals at us has demonstrated, by definition, that it has developed at least some capacity for curiosity and exploration. The existence of a SETI program is itself evidence that a civilization has interests, extending beyond its immediate survival needs. If we are doing SETI, presumably some other civilizations are also doing SETI. Civilizations that do SETI for long enough will eventually find neighbors, if any exist, and presumably that discovery will motivate further communication. There is also the argument from longevity. A civilization that has survived for 1 million years has presumably solved many of the problems that threaten our own: survival, energy, scarcity, resource conflicts, weapons of mass destruction, climate instability. 1 million-year-old civilization has had time to develop a mature perspective on its place in the universe. Whether that perspective would include an interest in communicating with younger civilizations is unknown. But the history of our own species suggests that curiosity about the wider world, an interest in encountering the genuinely unknown, is a deep and persistent feature of intelligent life. If other civilizations are curious about the universe, and if they have developed the technology to survey their stellar neighborhood, they have almost certainly already noticed Earth's biosphere. Our oxygen-rich atmosphere, unique in the inner solar system, is a billboard. Our technological civilization is now also radiating radio waves and has been for about a century. Any civilization within 100 light years knows we exist. And more advanced civilizations can probably infer our biological existence from our atmospheric chemistry alone, even at much greater distances. Whether any such civilization has chosen to send signals in our direction is the central unknown. The SETI assumption is that some have, or that their technological activity generates detectable signatures incidentally. The new observational era will test this assumption with unprecedented rigor. One possibility that gets occasional discussion in the scientific literature is that the signals, or the evidence of technological civilizations, are already present in our astronomical data archives, waiting for sufficiently clever analysis to reveal them. The history of astronomy includes multiple cases where important phenomena were hiding in existing data until someone asked the right question or applied the right analysis. Pulsars were lurking in radio observations before Jocelyn Bell spotted the characteristic signal that identified them. Gravitational lensing events had been photographed before anyone went back to look for them systematically. Dark matter had been inferred from its gravitational effects for decades, before anyone thought to do a comprehensive survey of galaxies to characterize its distribution. Could a technosignature be sitting in an existing dataset? Certainly possible. The HARPS dataset example mentioned earlier illustrates that data taken for one purpose may contain signatures relevant to another purpose. Infrared astronomical surveys taken to study stellar populations may contain the heat signatures of advanced civilizations that have not yet been identified as such. Time series data on stellar brightness taken to look for planetary transits might contain dimming patterns caused by structures that are not planets. The scientific community is increasingly aware of this possibility and is beginning to systematically read archival data with technosignature searches in mind. This is a relatively low-cost approach. The data collection has already been paid for, and it benefits from the computational and machine learning tools that have become available only in recent years. A technosignature that was too subtle to notice in the data as analyzed in the year the data was collected might be immediately apparent to a machine learning system trained on the full dataset in 2026. This is a genuinely exciting possibility, and it is being pursued seriously by multiple research groups. Perhaps the deepest question in all of this is not whether extraterrestrial intelligence exists, but what finding it would mean for humanity. This is not a scientific question in the strict sense, but it shapes the cultural and political context of SETI in ways that affect how the research is funded, communicated, and prioritized. A detection of extraterrestrial intelligence would be, without any doubt, the most significant discovery in the history of science. It would not merely answer a question that has puzzled humanity for millennia. It would restructure our understanding of our place in the universe more profoundly than the Copernican revolution, more profoundly than the discovery of evolution, more profoundly than the development of quantum mechanics and relativity. Every religion, every philosophy, every cultural tradition would have to grapple with the fact that mind and consciousness are not unique to Earth, the uniqueness that many traditions have attributed to human beings would need to be reconsidered in light of the existence of other minds, other cultures, other histories. This would not necessarily invalidate any particular tradition. Many theologians and philosophers have argued that the existence of other minds would be consistent with, and indeed would support, their views on the significance and prevalence of consciousness in a designed universe. But it would require genuine engagement, genuine wrestling with what we have found. For science itself, the implications would be even more concrete. A detected signal would tell us something about the transmission technology, whether radio or optical or something else, telling us that this technology is viable for interstellar use. It would tell us something about the distance, how far the signal traveled, telling us about the distribution of technological civilizations in our stellar neighborhood. It would tell us something about the longevity of civilizations, because a civilization detectable at a given distance must have survived long enough to develop the technology to transmit there. and it would tell us that intelligence is not unique to Earth, which is perhaps the most important single fact we could learn about the universe. What we might actually learn from the content of a signal, if the signal is decodable, is harder to predict. Some researchers argue that a signal would likely begin with mathematical content. Since mathematics is presumably universal among civilizations that have discovered physics, prime numbers, geometric relationships, physical constants, these would serve as Rosetta Stones for beginning to decode a more complex message. Whether we could actually decode the biology, the history, the culture, the science of another civilization from a signal received across interstellar distances is a genuinely open question. But the content matters less, in some ways, than the fact of detection. Even a signal of known artificial origin that we could not decode would transform our understanding of the universe. It would tell us we are not alone, and that knowledge, once obtained, cannot be unobtained. The scientists pursuing this research are not naive about the difficulty of what they are attempting. They know the universe is vast, and that our observing capabilities, however powerful, cover only a tiny fraction of it. They know that the assumptions built into any search strategy might be wrong in ways we cannot anticipate. They know that a century of radio silence, and now 6 decades of SETI, specifically, might mean that signals simply do not exist, or that they exist in a form we have not yet learned to recognize. But they also know that the alternative to searching is to simply not know, and not knowing, when the tools to potentially find out exist and are increasingly powerful, is a choice that science cannot accept indefinitely. The question is too important, the potential implications are too profound, and the instruments we are now building are genuinely capable of finding the answer. If the answer is findable, that is the position we are in today. The search has changed fundamentally from the simple, elegant radio surveys of the 1960s. It has expanded across wavelengths, across survey strategies, across theoretical frameworks. It has been integrated into the mainstream of astronomical research in a way that would have seemed impossible even 20 years ago. And it is now being carried forward by a generation of scientists who grew up with exoplanets as an established fact, who know the diversity and prevalence of other worlds with a confidence that Frank Drake could only imagine. The universe has been speaking in one form or another for 13.8 billion years. The light from distant stars carries information about their composition, their motion, their age, the planets around them, and possibly the civilizations on those planets. We are only now building instruments sensitive enough to read that information in full. Whatever we find when we read it will shape the next chapter of humanity's understanding of itself and its place in the universe. And that chapter is beginning now.